Okay, when we do energy problems, we have to be concerned with whether the force that we're dealing with is a conservative force or a non-conservative force. If the force is conservative, then the total energy change um, is going to be independent of the path taken. So a example of a conservative force field is gravity. Um, so for example, if I start with a book, let's say the book is up here at this location A, and it needs to end up at location B. And so the book could travel straight down like this path. We'll call that path 1. Um, and we saw in the previous video, or if you haven't watched that one, we can show that the change in the potential energy is equal to the change in the kinetic energy of the system. So if the change in potential energy is mgy and the kinetic energy becomes 1 half mv squared, we see that the velocity at the bottom is 2g squared root of 2gy. You'll notice that in this particular solution that I just made, I did not worry about which path, anything about the path I traveled. I only worried about how much energy I started with and how much energy I finished with. And I could have gone around like this by letting the book slide down, for example, a curved metal slide, or I could have thrown the book up in the air and have it return back to the point at the bottom, and it would have the same amount of kinetic energy or the same velocity when it got to point B, whether I followed path 1, 2, or 3. That is true because gravity is a conservative field. Any energy I put into the gravitational field, I can get back out. If I lift an object up 1 meter, when I bring it back down 1 meter, I get that same energy back. A non-conservative force doesn't follow those rules. And so a good example of a non-conservative force is friction. So a good example of a non-conservative force is friction. Here, take for example a block sliding down a plane. In the absence of friction, the velocity at the bottom of the plane is going to be given by that same relationship that we had over here, square root of 2gy, because all of the potential energy that the block starts with, it ends with a kinetic energy equal to that initial potential energy. But if there's friction present, then as the block travels down the plane a distance, let's call that distance x, there's a friction force applied up the plane like that as the block travels down the plane. So there's work being done on the plane by friction, which is equal to the parenthesis or the force F dot x in this case. And um, you'll notice that F and x point opposite directions to each other, which means this dot product is going to be negative Fx because the cosine of theta is 180 degrees, or sorry, the angle between f and x are 180 degrees. Therefore, the cosine of that angle is negative 1. So you'll notice that this minus sign in front of the work is significant. That minus sign means that energy is being taken out of the system so that the final kinetic energy is going to equal the initial potential energy plus the work done. So that's going to equal mgy minus fx. You'll see it's reducing, the friction is tending to reduce the amount of energy that I get at the bottom of the plane. Now, that's similar to if I push the plane block up the plane, then gravity is doing the same thing. Gravity, the work due against gravity is taking energy out. But the difference here is if I let the block slide down the plane and then I push the block back up the plane, when I push it back up the plane, friction is actually operating against me again. So when I move it up the plane a distance x, friction is again against me. So I lose energy to friction in both the down and the up direction. I never get it back. Friction is a dissipative force. It it dissipates energy out of the system into heat in most cases. So that's a case where it does matter what my path is. So if I went back to my original example with the block with the book coming down via these three paths, if there's friction present, then generally the longest path is it requires the most amount of or ends up with the least amount of energy left over. So you can see how I handled this in this particular equation here. I handled that as basically taking E final is equal to E initial plus any work done. In most cases, non-conservative forces will have a negative quantity of work, therefore the final energy will be less than the initial energy. So we can still write our equations as before with U final plus K final will equal U initial plus K initial plus any work done to the system. So for example, if I push on the system while it's going through its motions, that would generate positive work, and my final potential or kinetic would be greater than I started. If I let a non-conservative force like friction act, it's going to be negative. It's going to tend to pull energy out, and if I then reverse the process and take my starting point and go back to my initial point, if friction is still taking energy out, I will not end up back with the same amount of energy that I started with. Therefore, it's not a conservative field. So let's show that problem similar to the one we did in part one of this video. We have a 50 kilogram block, and I'm pulling it with a 100 Newton force and I drag it a distance of 20 meters. And the question is, after I've dragged it a distance 20 meters, how fast is it going? Well, let's throw in a little bit of friction this time, and let's say that the kinetic coefficient of friction is equal to 0.1. So again, here I'm going to work out my energy equation, but I now need to represent that there's a friction force present operating in opposition to my pulling here. So that friction force is going to equal 0.1 times the normal force, which is going to be 50 kilograms times 9.8. So this is going to equal, I think, um, about 49 newtons. Um, so I can look at my energy change then as U final plus K final equals U initial plus K initial plus any work lost in the system or work done by my force. So the work done um, is the 1/2 mv squared is going to equal zero. The potentials are zero in both of these cases. Initial kinetic energy is zero, plus the work done, which we can think of this as F net dot x. So 1/2 mv squared is going to equal the net force, which would be 100 newtons minus 49 newtons times the distance traveled, 20 meters. And I can now solve for velocity. V is going to equal 51 newtons times 20 meters times 2, all divided by 50 kilograms, and the square root of that. And you'll notice this number is going to be less than it was before because the amount of force that's actually contributing to the kinetic energy is less. This is one way of looking at it. The other way of looking at it is that we can think of this as equal to the work done by the 100 Newton force plus the work done by the friction force, which would have been 100 newtons times 20 meters plus minus 49 newtons times 20 meters because that work is negative. Maybe I better say it as minus 49 times 20 meters. And you'll notice that this is the same effect as the previous problem. Completing the solution for both of these methods, you can see that the end result velocity in either method are the same.